Myself, this is Dr. Shankaraiah, Associate Professor in Department Physics. In last couple of lectures, we have discussed something about quantum mechanics. First few topics about quantum mechanics, and today we will discuss about Schrodinger time-independent wave equation. So we know that in classical mechanics, the history of a particle is completely determined in the sense that we can, using Newton's laws of motion, we can determine the trajectory, or if a object is at a time t at this position, where it will be after certain time t plus delta t at what position. So that we can discuss using Newton's laws of motion. So classical mechanics, we can determine the trajectory of a particle. For example, here trajectory of this particle exactly. So it is deterministic exactly. But whereas in quantum mechanics, we cannot do so. We can only can arrive at relationship between observable quantities, but the uncertainty principle suggests that the nature of an observable is different in different atomic reality. That means in quantum mechanics there are uncertainties in obtaining the quantities, whereas in classical mechanics you can determine the dynamics exactly, deterministic. So we have defined wave function. Wave function is nothing but a quantity, complex quantity. Wave function is a complex quantity, which is a real part. You have real part and imaginary part. So a wave function is a complex quantity whose variations make up matter waves. Okay. So if you want to know the matter waves that are associated with a particle, then we can study its dynamics. So to understand the dynamics of this quantum particle, we are defining a wave function, which is a complex quantity, and the variations of this wave function will tell us about the matter waves associated with the particle. And we are denoting by this, we are denoting the wave function by symbol psi. So psi is wave function. So this wave function connects the particle nature and its associated wave nature. So if you can find out the wave function, then you can study both the particle nature and wave nature of a particle. So wave functions are generally complex, and it has both real part and imaginary part. And you cannot define any wave function. You cannot define any quantity as a wave function. Wave function must satisfy some properties. Okay, so these are the properties of wave functions. Okay, psi itself doesn't have any physical meaning. That means wave function is a complex quantity. So that is the reason why we define wave function as x plus iy. So if you directly determine, if you have only wave function psi, you cannot say anything about matter waves, because it's a complex quantity. It doesn't have any physical meaning directly. So that is why we are going to calculate its square of the absolute magnitude, which is mod psi square. And this mod psi square is proportional to the probability of finding the particle. So if you find out psi, it doesn't have any physical meaning directly, but you can calculate mod psi square, which is x square plus y square, which is real. So if you calculate mod psi square, it's a real quantity, and it tells us about the probability of finding the particle. Okay. So it is usually convenient to have mod psi square be equal to the probability density of finding the particle, rather than merely proportional to p, as particle exists somewhere over t. So we are defining the normalization for this wave function. So this is the normalization. This is called normalization. So this tells us about the tells us that summation over all the probabilities. Suppose if I have a box here, I have a box and I have trapped the particle inside this box. I can ask the probability of finding the particle at any point x inside this box. So if I sum up all the probabilities of finding this particle, then all the probabilities must be equal to 1. That means particle exists somewhere in this limit minus infinity to infinity, or if you define a box, you can define its diameter length 0 to L. So 0 to L, if you add up all the probabilities must add to 1. So this is called normalization condition. So this tells us that particle exists somewhere in the given limits. This wave function must be continuous and single valued everywhere. So these are the properties of wave functions. so are limitations of the wave function. So wave function must be continuous and it's be single valued, and its derivatives also must be continuous and single valued everywhere. And psi must be normalizable in the sense that, as we defined here, normalization condition. So if you integrate between the limits, all the probabilities must be add to 1. So these are some of the properties. So using now that we know all the limitations and properties of the wave functions, now we are going to derive this Schrodinger time independent wave equation. Time independent wave equation, one can generally have time dependent wave equation to study the dynamics, but here we are not doing the time dependent wave equation. Here we are looking at only time independent wave equation. So Schrodinger solved both time dependent and time independent wave equations of the particle, quantum particle. Here we are discussing only independent wave equation of Schrodinger. Okay, so to solve this Schrodinger time independent wave equation, we are going to first consider a particle of mass m. Okay, so we are considering this microparticle which is having mass m and it is moving with some velocity v. Okay, and this because we have discussed that de Broglie hypothesis that each particle is also going to have its wave nature, and we have said that these are matter waves. So if this is a microparticle having mass m and moving with velocity v, it must have its matter waves, and these matter waves we are going to represent by a wave group. Okay, so to understand these matter waves, we are defining the wave function psi for this particle of mass m. Okay, so now we do not know what kind of matter waves that are associated with this particle. So we are assuming that this is the kind of matter waves that are associated with this particle. So we are considering psi as psi naught sine omega t minus kx. So now we are partially differentiating this equation twice. We are trying to look at the wave equation. So wave equation in general is a second order differential equation. So I am going to differentiate this psi 2 times. Okay, so do the first derivative. So dou psi by dou x. What is dou psi by dou x? Dou psi by dou x is psi naught cos omega t minus kx, and differentiation of this minus kx is minus. So that is minus k psi naught cos omega t minus kx. So this is the first differentiation of wave function with respect to psi. Then do the second differentiation. Okay, second differentiation is dou square psi by dou x square is equal to minus k psi naught. Differential of cos is minus. So minus sine omega t minus kx. And then again differentiation of this minus part minus kx is again minus k. So minus plus again minus. So that is equal to minus k square psi naught sine omega t minus kx is nothing but psi. Okay, so we basically have minus k square psi. So dou square psi by dou x square is equal to minus k square psi r. Dou square psi by dou x square plus k square psi is equal to 0. So this is the second order differential equation we got after differentiating the wave function twice. Now we know what is this propagation vector k. Okay, so we are going to substitute this propagation vector in this equation. Okay. So yeah, so k is wave vector given by 2 pi by lambda. We know this k is 2 pi by lambda. So whatever equation we have before, so this is the equation dou square psi by dou x square plus k square psi is equal 0. So in this place of k square we are substituting 2 pi by lambda. So basically, so dou square psi by dou x square, so k square is basically 4 pi square by lambda square into psi is equal to 0. Okay, so these are the two differential forms of classical wave equation now. But de Broglie said that each particle is going to have wave nature and its wavelength is lambda given by h by m. So we are going to substitute lambda in this equation. So basically lambda is equal to h by mv. We are going to substitute here, right? So when we substitute that, dou square psi by dou x square plus 4 pi square by lambda square is h square by m square v square into psi is equal to 0. Okay, so that will be dou square psi by dou x square plus 4 pi square m square v square by h square into psi is equal to 0. Okay, so this is what we got. Dou square psi by dou x square plus 4 pi square m square v square by h square into psi is equal to 0. So we are going to substitute this m square is v square using the total energy equation. Okay, so this is what we got, right? In the previous slide we have actually calculated that, but now here I am defining a new variable h cut which is equal to h by 2. So that is why h square by 4 pi square is removed by substituting h cut square, because h cut square is h square by 4 pi square. Okay, so that is why h cut square is here h square by 4 pi square is gone. Okay, so now I want to get what is m square v square. To get this m square v square, I am using the total energy of a particle. Total energy is defined as kinetic energy plus potential energy. So kinetic energy is half mv square. I do not know what kind of potential is there, so I am taking the potential as v. Okay, so using this total energy E is equal to half m square plus v. I'm multiplying this equation, so let me write down here. Okay, let me remove this. So basically what I have is E is equal to half m square, half mv square, right? Not m square. So half mv square plus, this is potential, capital V. Okay, so for this equation I am multiplying with m on both sides. So me is equal to half m square v square plus, this is potential, capital V. Okay, so now I am taking 2 this side. So 2me is equal to m square v square plus 2. Okay, there is a m because I have to multiply m on both sides. So mv. Okay, so now I want to get what is m square v square. So m square v square is equal to, I'm going to take v this side. So 2m is constant, 2m into e minus v. So this is what I got for m square v square. So I'm going to substitute this here. I'm going to substitute this m square v square in this equation to get the complete equation. Okay, in terms of energies and potential energy and total energy. Okay, so now so I'm going to substitute that m square v square which I have here. So I've substituted m square v square is equal to 2m into e minus v. So finally I came up with this time independent Schrodinger wave equation in one dimension. So that is dou square psi by dou x square plus 2m into e minus v by h cut square into psi is equal to 0. So this is the time independent Schrodinger wave equation in one dimension, because we have only x. This is in one dimension, one spatial dimension. Okay, because we have only x. If you want to write down in 2 dimension and 3 dimension, you will have 2 more variables in 3 dimensions. So in 3 dimension, this is the equation: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m into e minus v by h cut square into psi is equal to 0. Or I want to replace all these 3 differentials by Laplacian operator del square, which is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So del square psi is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square into psi. Okay, so this is called Laplacian operator. Okay, so finally we came up with this equation in 3 dimensions. So dou square psi del square psi plus 2m into e minus v by h cut square psi is equal to 0. So this is the time independent Schrodinger wave equation in 1 dimension, and similarly in 3 dimensions. We can extend this into 3 dimensions and 2 dimensions. Okay, in 3 dimensions we have 3 variables x, y, z, but in 2 dimension we will have only 2 dimension we have only 1 variable, 2 variables x and y. Okay, so we have derived, we have looked at the derivation of time independent Schrodinger wave equation starting with a particle, microparticle of mass m moving with velocity, and then we have assumed that there is a wave function associated with this particle, because each particle is going to have its wave nature, and then we have assumed this progressing wave kind of wave function, and then we have differentiated the equation, got the second order differential equation, substituted the de Broglie wavelength hypothesis, and then finally we came up with this time independent Schrodinger wave equation in 1 dimension and 3 dimensions. Okay, so now we are going to apply this time independent Schrodinger wave equation to a problem which is called as a particle in an infinite potential well. So we are going to study the dynamics of the particle which is trapped in an infinite potential well. So this is the box. Okay, so this is the box, and so this is a particle that is trapped in this box, and we are defining the potential V of x for this box. So we are going to solve the time independent Schrodinger wave equation for this particle in infinite potential well and look at the wave functions that are associated with this particle. Okay, trapped particle, and the length of the box is a. Okay, so length of the box is given as a. So I am defining the potential for this particle. So V of x is equal to 0, 0 less than or equal to x less than or equal to a. So that means inside the box the particle can move freely, so because the potential is 0. And outside this box, for example, x greater than a and x less than 0, potential is infinite. Potential is infinite, so the particle is basically trapped and it can move freely only inside the box. It is not allowed to escape the box, for example. So then now we are going to solve this Schrodinger wave equation for this particle trapped in an infinite potential well. So this is the Schrodinger wave equation in 1 dimension, right? Dou square psi by dou x square plus 2m into e minus v by h cut square into psi is equal 0, and we know what is h cut. H cut is nothing but h by 2 pi. Okay, so now particle inside the well. Inside the well, we define the wave potential as 0 inside the well. So substitute this v is equal 0 in this equation, time independent Schrodinger wave equation. We get dou square psi by dou x square plus 2 m e by h cut square psi is equal to 0. Okay, so now this is the second order differential equation again. So dou square psi by dou x square plus I can define a quantity k square is psi is equal 0, where k square is equal to 2me by h cut square. You can define k, or you can write this as alpha square also, because there is another k which is propagation vector. So to avoid the confusion, I am defining this k as alpha square is equal to me by h cut square. So solve this differential equation. When you solve this differential equation, d square plus alpha square into psi is equal 0, you will come up with roots plus or minus, and you can write this as this is one of the way of writing the solution, or you can write in terms of exponential. Psi of x is equal to a e power minus I alpha x plus b e power plus I alpha x, because you are going to get plus or minus I alpha as the roots. Okay, so this is one way of writing the solution, and another way of writing the solution is a sin kx plus b cos kx. I have used k, so I am going to write this as alpha. So this is the solution of the differential equation. When we consider the particle inside the well, the potential is a. Okay, so a sin alpha x plus b cos alpha x. So this is the wave function we got, right? So now let us try to find out the unknown constants. We already got the wave function, but unfortunately there are two unknown constants, right? So two unknown constants a and b. So we have to find out what is a and what is b and what is alpha. We already know. So if we can find out a and b, then we completely get the wave function. So then our work is done, right? So our aim is to find out these unknown constants. So to find out the unknown constant, I am using the boundary conditions. Okay, boundary conditions. So the first boundary condition is this. This is the first boundary condition. Psi of x is equal to 0 at x is equal to 0. That means the wave function must be 0. Wave function must be 0 at the boundaries. Psi of x is 0 at x equals 0 and psi of x is equal to 0 at x equal to a. So psi must vanish. Inside psi can have any value, but at the boundaries, that means x is equal to a and x equal to 0. So these are the two boundaries. The wave function must vanish at the boundaries so that it satisfies the normalization condition. So this is the first boundary condition and this is the second boundary condition. So we are going to use these boundary conditions to find out these unknown constants a and b in this equation. Okay. So to do that, first we are applying the first boundary condition. Psi of x is equal to 0 at x equals. So if we apply this in the solution. Psi of x is equal to 0 at x equals, so a sine, this is k or alpha, you can take it as alpha, x is equal to 0 here also, x is equal to 0, so a sine 0 is 0, cos 0 is 1, so you basically get 0 is equal to 0 plus b into cos 0 is 1. So basically you get b is equal to 0. So this one of the constant we are able to find out using the boundary condition. Second one, we are going to substitute second boundary condition in the equation. So 0 is equal to a sine x is equal to a, so a sine alpha a plus b cos alpha a, so b is 0, so you can just, you don't have b term, so this term here you don't, 0 is equal to a sine alpha into a plus b cos, but b itself is 0, right? So no second term, only first term, so a sine alpha a is equal to 0. So if you a sine alpha is equal to 0 means you can have a is equal to 0 or sine alpha a is equal to 0. When any of these two terms can be 0. If you take a is equal to 0, a is equal to 0, b is equal to 0, the wave function is 0, which is not true. So we are going to equate sine alpha a is equal to 0. Okay. So what happens when we take sine alpha a is equal to 0? So sine x is 0 for what values of x. So if you know for what values of x sine x is 0, then we will find out what is alpha a. Okay. Yeah. So we know that sine of x is equal to 0 for x is equal to 0 and n pi. 0 and n pi. So that is why this alpha a is also, sine of alpha a is also equal to 0 for alpha a is equal to n pi. Okay, so alpha a is equal to n pi, so that means alpha is equal to n pi by a. So we are also now we are able to calculate what is alpha using the second boundary condition. So I am going to substitute this in the equation of wave function. So psi of x is equal to a sine alpha is n pi by a, where a is the length of the box, so n pi by a into x. I used to have b term also, but b is 0. Okay, b is equal to 0, so I do not have the second term, I have only this term, and this is the wave function I got. So still there is this unknown constant a. Still I am not able to find out this unknown constant a. Okay, still there is this a. If I can find out this a, then I will have the complete wave function. So I need to find out what is a. Okay, so to find out a, I am differentiating this equation 5. So this is the equation 5. I am partially differentiating this equation twice. So first psi of x is equal to a sine n pi by a into x. Okay, so let us first differentiate this equation. So dou psi by dou x is equal to a cos n pi by a into x, and there is another n pi by a. So this is the first differential, and let us differentiate it again. So second differentiation, dou square psi by dou x square is equal minus a sine, because sine differential minus, so n pi by a into x, and this is n pi by a, and again n pi by a, so that is n pi by a also. Okay, so basically I have, I have this dou square psi by dou x square is equal to minus a sine n pi by a into x into n square pi square by n square pi square by a square. So I am taking out this side, so dou square psi by dou x square plus n square pi square by a square, and a sine n pi by a into x is basically psi of x. Okay, so that is why I finally have this kind of equation, dou square psi by dou x square plus n square pi square by a square into psi is equal to 0. Okay, so now I am going to compare this equation with the previous equation with alpha. Earlier I have one equation in the beginning, right, which is dou square psi by dou x square plus 2me by h cut square into psi is equal to 0. So when I compare these two equations, I find out that 2me by h cut square must be equal to n square pi square by a square. Okay, So from this I can write out what is energy E. Energy of this particle E is equal to n square pi square h cut square by 2m a square, or I can substitute what is h cut square. H cut square is h square by 4 pi square, so n square pi square by 2m a square, and h cut square is h square by 4 pi square. So pi square will cancel out. So what I'll find out is n square h square by 4 into 2 8m a square. This is energies. So energies of a particle in different energy level. N is the index of the energy level. So n can be 1, 2, 3, so on and so forth. So energies of the particle in different energy levels is given by n square h square by 8m a square. Still we couldn't find out what is A, so we still have to find out this unknown constant A, so that we can write down the wave function completely, right? So without any constants A and B. So we found what is B. B is equal to 0, but still we have A. Okay, so I equated the two equations, and then I find out that the energies of the particle associated with the particle in different energy levels is given by n square h square by 8m a square, right? So where h is Planck's constant, and m is mass of the particle, and A is length of the box which we consider. Okay, so yeah, fine. So these are the energies associated with this particle. Energies associated with the microparticle, in different energy levels. Okay. So we are now able to find out the energies of this microparticle in different energy levels. So n square h square by 8m a square, and we know what are all these parameters, right? So still we have to find out this unknown constant A to write down the wave function psi. So finally we got these energies, still not wave functions. So we have to find out the wave functions. Okay, so to find out the wave function, first we need to find out this A, so that we are going to calculate using this normalization condition. Okay, so this is called normalization condition. We know that we have defined minus infinity to infinity mod psi square dv or dx must be equal to 1 in one dimension, right? But here the dimensions of the box is 0 to A. Okay, so that is why we are taking the normalization condition as 0 to A mod psi square dx must be equal to 1. So we have to substitute psi. What is psi? So psi is already given by psi is, we have calculated psi, so we are substituting psi, right? Yeah. So psi is equal to psi of x is given by a sine n pi by a into x. So this is psi, so substitute psi here. So psi square is a square sine square n pi by ax into dx equal to 1. Okay, so this sine square we are going to write in terms of cos 2x. So sine square x is equal to 1 minus cos 2x by 2. Okay, so 1 minus cos 2 x is this n pi by a into x. So 1 minus cos 2x by 2. So there is a 2. So I must have 2 here. Okay, by 2 into x is equal to 1. So integral 0 to 1, 1 minus cos 2x by 2 into dx equal to 1. So now I'm going to write down the integral for all these. Okay, so let me erase this. Okay, so I have separated the integral. So basically a square by 2 is there outside constant. So 0 to a dx minus 0 to a cos 2 n pi by a into x again dx, all must be equal to 1. So integral dx is x, so that is why I have here integral a square by 2 outside, which is a constant. So I have x, and then minus there is a, when I do integral I get a n pi by a by So that it will get, I'll basically get integral is cos is sine. So let me write down sine 2n pi by a into x by 2n pi by a. So that will become a by 2n pi here, and sine 2n pi by a into x all must be equal to 1. Okay. So that is how I get this. So now I'm going to substitute these limits. The limits are 0 to a. So let us substitute the limits. Okay. So when I substitute the limits between 0 to a square by 2 is outside the constant. So a and this all becomes 0 here, because sine a, if I substitute a here, a will cancel, sine n pi is 0 and sine 0 is also 0. So basically the second term will all 0. So only I have x, which is 0 to a. So I just got this. So a square by 2 is equal to 1. A square by 2 is equal to 1. That means a square by 2 into a is equal to 1, or a square is equal to 2 by a, or a is equal to square root 2 by a. So that is how I got this. Okay. So finally I got this constant a, which is equal to square root 2 by a. So therefore the normalized wave function is given by this. Psi of x is equal to square root 2 by a sine n pi by a into x. So these are the wave functions associated with the particle, and we have also derived energies n square h square by 8m a square. So these are the energies. So these are our energies are also called as eigenvalues and eigenfunctions for a particle trapped in an infinite potential well. So we have to so you can ask, there can be different ways of asking this question, particle in infinite potential well. So particle trapped in an infinite potential well are a 1D box, or so then you have to start from here, this, first you have to define the potential, draw this figure where v is equal 0 inside and v is infinite at these boundaries, and length of the box is a. So x is equal 0 here and x is equal to a. So there are the two boundaries, and define the potential v of x. And once you define the potential, and then you apply this, solve this Schrodinger wave equation inside the box, and you get a solution and try to find out these unknown constants a and b, and in the process you will find out the energies, and then using normalization condition you are going to calculate this a. One important point is that how do you get these unknown constants a and b, which is very important, that you need to use boundary conditions. Okay, so using boundary conditions we are going to calculate one of the constant b, which is 0, and then the another constant a is calculated using normalization condition. So finally we got this wave functions and energies for the particle trapped in an infinite potential well. So let us plot these wave functions and its absolute square magnitude for different energy levels. Okay, so this is n is equal to 1, and this is n is equal to 2, and this is n is equal to 3. So this is psi of x versus x in different energy levels, but psi of x has no direct physical meaning, so we are calculating mod psi of x square. Right? So mod psi of x square tells us about the probability of finding the particle. So you can see that it is positive throughout, because mod psi square is a probability of finding the particle in different energy levels. You can see in different energy levels, red is 1 and green is 2 and blue is 3. So we have calculated the probability of finding the particle in different energy levels. So a trapped particle cannot have any arbitrary energies as a free particle. Because of the confinement, it can have only discrete energies. Okay, and a trapped particle cannot have zero energy also, because since the de Broglie wavelength of a particle lambda is h by mv, if you take v is equal 0, it is infinite wavelength, so you cannot calculate this infinite wavelength. So the particle must have at least some kinetic energy, so that we can measure the wavelength. And E is equal 0 is not allowed for the particle, whereas in classical particle you can use even E is equal 0 and any arbitrary value for classical particle, and you cannot experience this because the constants that are there in the equation are very small, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.